Okay. uh, so can a particle be trapped in a magnetic field? This is our question for the today. We have to find a force that can trap a particle in a magnetic field. So we consider magnetic field pointing in z direction and whose magnitude varies in z direction. So if the field is symmetric along the axis, we consider that over b theta is 0 and partial theta equals 0. And this has a cylindrical symmetry, so we can write it as b equals b of r unit vector plus b of z unit vector. So how does this configuration give rise to a force that can trap a particle? We can obtain b of r from del dot b equal to 0. And we know that in cylindrical polar coordinates, del dot b can be written as 1 over r partial r b of r plus partial z b of z equals 0. Or we can write it as partial r b of r equals minus r partial z of b of z. So if we are given that at r equals 0, our magnetic field does not vary along z direction. So we can write this above expression as r b of r equals minus integral of from 0 to r partial z bz d of r equals, as partial z bz by partial z does not vary, so we can treat it as a constant at r equals 0, and over integral is over r, so we can have expression of the form r b of r equals minus 1 over 2 r square partial z of b of z at r equals 0, or we can write it as p of r equals minus 1 over 2 r partial z of bz at r equals 0. Now we have obtained our magnetic field in radial direction in terms of b of z, and from this br we can use it in order to find Larmor force on the particle. So if we find to find the Larmor force on a particle, we know that our force Larmor force is q v cross b, and if we write it in determinant form, we can find the components of Larmor force. F of r equals q v theta bz minus vz b theta. F of theta q minus vr bz plus vz b of r. F of z equals q vr b theta minus v theta b of r. As we have mentioned earlier that over b theta is 0. So the terms containing b theta in f of r and f of z will be cancelled out. And we are left with the four terms, that is f of r equals q v theta bz. This is our first term. F of theta equals q minus vr bz. This is our second term. Our first term and our second term just give the gyration of the particles along bz, and the third term is vz b of r. This vanishes on the axis and causes a drift in the radial direction. Our fourth term, that is v theta b of r, this is of interest. If we substitute b of r, the value we have obtained earlier in this expression, into f of z equals 4. So we can obtain the relation f of z equals minus q v theta b of r equals q v theta r over 2 partial z of bz. So if we take the average over one gyro period and put v theta equals minus plus v perpendicular and over r equals Larmor radius, we can have f of z equals minus plus q over 2 r. We have put v perpendicular in terms of v theta in terms of v perpendicular partial z of bz. So this force is known as mirror force, where minus plus sign arises because the particle has opposite charge and they orbit in opposite directions. So above expression, this can normally be written as f of z equals minus plus 1 over 2 q v perpendicular square over omega c partial z of bz, where we have used the value of RL in terms of omega c, and we know that omega c is qb over m, so we can write it as minus 1 over 2 mv perpendicular square over b partial z of bz. So if we can define a new term a magnetic moment, that is mu equals 1 over 2 mv perpendicular square over b. So we can write this f of z equals minus mu partial z of bz. And in 3D, we can write this force as F parallel equals minus mu partial SB, where partial S is the element of length along B, and F parallel shows us that we are moving in the direction of magnetic field, that is along the Z direction. Ji Aruba. Okay, so let we talk about magnetic moment mu. That is our first adiabatic invariant. As particle moves into regions of stronger or weaker magnetic field, Larmor radius changes, but mu remains invariant. To prove this, consider component of equation of motion along magnetic field. That is, we have F equals ma or F equals m dv by dt. And we know that if we are moving along parallel direction and we are considering the force in parallel direction, so m into a is dv parallel by dt. And we know that we have already mentioned that f of z equals minus mu partial z of bz. So we can write it m dv by dt equals minus mu d by ds of b. If we multiply both sides with v parallel, so we can write it m v parallel d by dt of v parallel equals minus mu v parallel d by ds of b. And we can take this m and v parallel into the derivatives, so we can write it d by dt of half of m v parallel square equals minus mu ds by dt db by ds, where we can see that if we differentiate this equation, we will exactly get this mv parallel dv parallel by dt equals minus mu ds by dt dv by ds. So we can cancel this element along b direction, ds by into ds. So we can left with minus mu d by dt of b. So particles energy must be conserved. That is d by dt of half of mv parallel square plus d 1 by 2 mv perpendicular square must be equal to 0. And we know that mv perpendicular square into 1 by 2 equals mu into b, that we have already mentioned in our this equation. So we can write it d by dt half of mv parallel square plus mu b equals 0, or minus mu dv by dt plus d by dt of mu b equals 0. From where this mu d by dt b comes, this comes from this equation, that is d by dt half of mv parallel square equals minus mu dv by dt. So we can write this expression as minus mu dv by dt, and we can differentiate with respect to mu and with respect to b. Mu db by dt plus b d mu by dt equals 0. First and second terms can be cancelled out, and we are left with b d mu by dt equals 0. As we know that b does not equal to 0, so this implies that over du by dt equals 0. That is, if we integrate this, we can see that over mu is constant in time, that is, it is invariant. And this invariance of mu is a primary scheme for plasma confinement, that is known as magnetic mirror. So as the particle moves from weak field to a strong field, it sees B increasing, and therefore it's to remain for mu to be constant. If B increases, over V perpendicular must increase. As B increases, V perpendicular increase, so that our mu remains constant. So we know that energy should be conserved as V perpendicular increases. So in order to for the energy to be conserved, over V parallel should be decreased. that is the velocity, the component of velocity along the magnetic field lines should decrease. If our magnetic field is high enough in that region, our V parallel eventually approaches to zero and the particle is reflected back to the weak field, and this gives rise to a magnetic mirror. Such type of magnetic mirror is seen in magnetospheres, planetary magnetosphere, magnetic bottles, coronal loops, etc. So, what is the consequence of invariance of mu? We can see that we have two regions of magnetic field. First region, we consider that here our magnetic field is weaker, that is, we consider it B naught. And when we move towards the z direction, our magnetic field is becomes stronger, and we say that there our magnetic field is B1. As the particle moves from weaker to stronger magnetic field, we consider that in a weaker field, our particle has velocity V naught, and in stronger field, it has a velocity of V1. And we know that the magnetic moment is conserved. So conservation of magnetic moment implies that in the weaker field, half of m v naught square over b should be equal to in the stronger field where mu should be equal to half of m v perpendicular square over 2v1. So as our magnetic field increases, the perpendicular component of particle velocity increases, and particles move more and more perpendicular to b because parallel component of the velocity decreases there. However, since we have E is 0, we do not have an external electric field that can give energy from outside to the particles. So the particle energy cannot increase. So this is the case where V perpendicular increases and V parallel decreases, and the particle slows down in its motion along the field lines. So if field convergence is strong enough at some points, the particle may have V parallel equals 0. And at that point, the particle will be totally reflected back from the due to the magnetic field. Let me consider this and say it as that B1 we have V parallel equals 0. From conservation of energy, we know that if we have velocity, initial velocity V naught, and final velocity we have V parallel and V perpendicular, then V naught square should be equal to V parallel square, 1 parallel square plus V1 perpendicular square. And we know that V1 parallel equals 0, so V naught square should be equal to V1 perpendicular square. Using half of mv naught square over b naught equals half of mv 1 square over b1, we can write the ratio of b naught over b1 to be v naught perpendicular square over v1 perpendicular square, or we know that v1 perpendicular square equals v naught square. So b naught over b1 can be written v naught perpendicular square over v naught square. And if we look at this figure, that is, we are moving along magnetic field, so component of velocity is v parallel along magnetic field, and the other one is v perpendicular. And if the theta is the angle with to the initial direction, so we can say that over v perpendicular over v naught should be equal to sine of theta, and so we can write b naught over b1 equals sine square theta. If we have a smaller theta, particle will mirror in the regions of higher B. That is, when there is a higher magnetic field, particle will be reflected back. But what if our theta is too small? If theta is too small, then perpendicular component of the velocity will be much smaller. So the particle will not be reflected back, and it will escape from this region. So let we define the mirror ratio. That is, we can say that Rm equals Bm over B naught, where we have considered that over Bm is equal to B1 for some cases, and B naught is initial weaker field. For small theta of a confined particle, sine square theta should be equal to B naught over Bm, or we can write it as 1 over Rm. So this defines the region in velocity space in the shape of a cone. Or this cone is called as loss cone. We can see that there is a cone. So this is over theta m. So what is relation for theta and theta m? If over theta is greater than theta m, that is we have particle in this region, then our particles will be reflected back due to the magnetic field. That is, our V perpendicular will be larger than V parallel. But what happens if our theta is smaller than theta m? Then will be in the region where our V perpendicular is smaller than V parallel. So the particles will not be mirrored and will move towards the magnetic field, and they will leave the region of the magnetic field along z direction. So this is known as a loss cone. That is, whenever we are in this region where over theta is less than theta m, then the particles will be in the loss cone and they can be scattered and leave the region of the magnetic field. So we can see that the opening angle, it does not depend upon the charge or the mass of the particle. So as electrons and protons are lost equally if the plasma is Coulomb-less. But what happens is there are Coulomb in the plasma. Then Coulomb scattered electron will be more Coulomb scattered than the ions. Thus electron will be scattered out of the mirror trap more quickly than ions. So let we next discuss about time varying magnetic field. We have already discussed about time varying electric field. What happens when we allow magnetic field to vary in time? In the Larmor force is always perpendicular to be a magnetic field itself cannot impart energy to a charged particle. However, associated with the magnetic field, there is an electric field that is del cross E equals minus B dot, and this can accelerate the particles. So if we consider that over V perpendicular equals dl by dt to be the transverse velocity, and L being the element of path along the particle trajectory, with V parallel being neglected, taking the scalar product of the equation of motion with V perpendicular, we can write it as d by dt of half of mv perpendicular square equals qe dot v perpendicular. And if we put the value of v perpendicular into this equation, we can write qe dot dl by dt. And if we look for the change in one direction, we can write it as delta of half of mv perpendicular square equals 0 to 2 pi over omega c qe dot dl by dt of dt. If the fields changes slowly, then we can replace time integral by the line integral over unperturbed orbits, and delta of half of mv perpendicular square should be integral qe dot dl, and we can apply Stokes theorem here to write it as q integral del cross e dot ds equals minus q b dot ds, where s is the surface enclosed by the Larmor orbit and has a direction given by right hand rule when the fingers point in the direction of v. So if b dot ds is less than 0, it will be for ions, and if b dot ds is greater than 0, we will be considering electrons. So we can write this expression delta of half of mv perpendicular square equals plus minus q b dot, and integral of ds will give us surface area pi rl square, and we know that rl can be written in terms of m v perpendicular omega c and qb. So we can write it plus minus qb dot pi v perpendicular square over omega c m over plus minus qb, and this can be written half of mv perpendicular square over b 2 pi b dot over omega c. And we have already discussed that half of mv perpendicular square over b is known as magnetic moment. So we can write it as delta of half of mv perpendicular square equals mu delta b. So since the left hand side over this half of mv perpendicular square, we have already discussed this is mu b. So we can write delta of mu b equals mu delta of b, and if we again open it, we can write this delta mu equals 0. That is, magnetic moment is invariant in time varying magnetic field. As the field varies in strength, the Larmor orbit expands and contracts, and particles lose and gain energy, and this exchange of energy between the particle and the field is described very simply by above expression. So the invariance of U allows us to prove easily the following well-known theorem, that is, the magnetic flux through a Larmor orbit is constant, and we can prove it as we know that phi is b pi equals b into s, and we know that s is pi r square. So we can write phi is equals b pi v perpendicular square over omega ski, and we can write this term b pi v perpendicular square, b can be cancelled out with b square, 2 pi m over q square into half of m v perpendicular square over b, and this is equal to 2 pi m over q square mu. So if over mu is constant, then over flux should be constant, that is, magnetic flux through a Larmor orbit is constant. This property is used in plasma heating known as adiabatic compression. Here is the figure shows how this is done. We have 4 coils A, B, C and D. Into coils A and B, we have a region of stronger magnetic field and weaker magnetic fields. So if we inject plasma from A and B, it can be trapped in this region, and if we increase magnetic field, so our V perpendicular must increase in this region. The heated plasma can then be transferred to the region C and D if we further pulse from region A, and in this region we can increase the strength of the magnetic field, and if we increase the strength of the magnetic field, the plasma can be heated. And adiabatic compression can also be used successfully into toroidal plasma and an essential element of laser fusion schemes using either magnetic or inertial confinement.